Now we're going to dive into big O notation. So big O notation is one of the concepts in data structures and algorithms. And these are concepts that is going to help us understand how efficient a solution is and in terms of time. So we're going to go and understand the time complexity of algorithms and how we go by that. We're going to go and look at some common notations such as O of 1, O of n, and a few more notations there. So starting with time complexity, to understand time complexity, it is simply a way to express how an algorithm's runtime scales with the input size. So we're basically checking out how does the amount of time that a program takes change according to the size of the input. So an example is sometimes if the input is big, then the runtime also increases. That is one way of checking out the time complexity. And this helps us in terms of predicting the performance of an algorithm as the input grows. So we to be a bit more efficient, we don't want to be in a situation where as the input increases, at the same time you find that the runtime is also increasing. So we try to sort of minimize those situations. Now, to understand time complexity, it basically allows us to compare algorithms so that we can choose the most efficient one for different tasks. So, of course, we do want the one that is a bit more time efficient with the task that we're going to be doing. Right. On top of that, one other thing we need to understand is big O notation. And just as a definition, this is a mathematical notation that describes the upper limit of an algorithm's time complexity. So it basically categorizes algorithms by their worst case scenario. An example that we can use here is, let's say you're trying to search for an item in an unsorted list of 100 elements. So let's make an assumption that this is an unsorted list of 100 elements that we have here. The time that it's going to take depends on how many elements we need to check. So in the worst case here, it's going to take 100 checks, which is going to be now the worst case time complexity. And it's we note that with big annotation. So an example is, for example, if the element that we're looking for is 0, and the 0 is the one that is at the end. So now it has to go through 100 checks until it gets to 0. That is the worst case scenario. Best case scenario is that the moment it starts checking, the first element it finds out is the element that you are searching for. So that is what we do with big O notation. Now, there are some common big O notations that are really important that we need to understand. And the first one is what we refer to as constant time. So we have constant time, and we denote constant time by just O of 1. So like this is what we refer to as constant time. And in constant time, an algorithm runs in constant time because it basically does not depend on the size of the input. So no matter how large the input is, the runtime still remains the same. So an example here is when you are accessing elements in an array, and its index is going to be O of 1 because you directly jump into the location. So for example, if you're trying to access elements in this array, in the array that we have here, and you already know the index of that element that you're trying to search for. So if this array was called, let's just call it array. So you are the array, then you specify the index of, you know, the element that you're looking for is at index 8. So if this is how you are searching for it, then this is going to take constant time because you're directly jumping into the location of the element that you're looking for. Apart from constant time, we also have linear time. So we have linear time, and we represent linear time by O of n. So we represent linear time by O of n, like this. And for linear time, this is when an algorithm basically its runtime grows proportionally with the size of the input. So as the size of the input grows, basically the the time also, the time that it takes to access elements also grows. So an example is in a simple for loop, you have to iterate through each element in a list, and that is going to take off n time because n is the number of elements. So an example is if you're iterating through this and you have n elements, so you have n elements in your list and you're iterating through the list, of course, the iteration is going to depend on the number of elements that you're trying to iterate through. So an example is just a simple for loop. It's going to take linear time because it's going to depend on the number of items that you have. So if you're iterating through, let's say 5 elements, then you increase to 100 elements, the number of iterations is going to increase, of course, hence more time. The other one is what we refer to as quadratic time. So we have quadratic time, and we represent quadratic time by O of n squared. So let's represent this like this. Okay, let's just do this O of n squared, just like that to understand that. So it's going to take the time complexity is going to be O of n squared. This notation means that the runtime grows exponentially with the input size. So if the input doubles, then the runtime increases 4 times. Yeah. So not if the input doubles. So if the input doubles like that, then runtime also increases 4 times. So there's 4x runtime. Now, an example of this is when you're dealing with a nested for loop. So in nested for loops, where you're basically comparing each item with every other item. So like if you're doing a basic bubble sort, then you'll have a time complexity of O of n squared. So it's basically if you have another simple example is when you're dealing with an array like this one, and let's say it has an array of arrays, and you are writing two for loops rather, one for loop to iterate through this array, and another for loop to iterate through the other arrays that are in there. So if it is an array of arrays situation, then you're going to need a nested for loop. In that case, the complexity is going to be in quadratic time, which is going to be of n squared. So if you notice an example of a program that has a nested for loop, so it has maybe one nested for loop, then it's going to take off n squared in that case. Now, if another for loop also is there, then the runtime is also going to increase as a result of that. The other one is what we refer to as logarithmic time. So we have logarithmic time, and for logarithmic time, represent it as O of log n. So we have O of log n. And for logarithmic time, basically an algorithm's complexity reduces the problem size with each step. So basically, if you are if you're dividing the input in half repeatedly. So an example is if you're doing a binary search, then it's going to take O of log n because each step reduces the problem size by half. Now, if you don't understand binary search and some of these algorithms, that's okay because we're going to be covering them in the future videos as well. So if basically how it works is the moment you're basically dividing everything. So it's in some sort of a tree, then basically the input sort of keeps halving repeatedly, right? So if you have, let's say, n, then the next input is going to be half of n. So going to be n divided by 2, half of n. Then the next is going to be n by 4. It keeps on halving basically. Then n that's going to be by 8 and on and on. So that is logarithmic time. And basically, so far, what you've covered is the basics of big O notation, understanding basically what big O notation is, what time complexity is, and some of the common notations. So such as constant time, linear time, quadratic time, and logarithmic time. So thank you for watching this far. In the next video, we're going to dive a little bit deeper as well into this time complexity. Cheers.